I take back every nice thing I said about the Video.js guys. So anyway, no, thanks so much, Lee, Coursera guys, for coming down. Up? Coming up. Anyway, this is Alex from the Google team. So he's going to talk about AAC. And he's actually been coming to Meetup for like 6 months now. So most of you guys probably also know him pretty well. But anyway, Alex.
All right. I'm Alex Converse. I work for Google on the VP9 team, but I'm here tonight to talk about audio, AAC in particular. I used to work for YouTube on the transcoding team focusing on audio-related projects. And before that, I wrote a big chunk of the FFmpeg AAC decoder. So AAC has this ecosystem of crazy profiles and extensions and whatnot, and it's not really clear what these extensions and profiles bring to the table and how they work, so I'm going to try to elucidate that. So first, the basics of digital audio. Audio in the real world is like a continuous waveform of air pressure going up and down and up and down. And in the digital world, we capture this in time by sampling, and the idea is that you get a snapshot of the waveform value once per your sample rate. You have to sample at least twice as fast as the highest frequency you're looking for. So if you want to capture 22 kilohertz, you need to sample at 44 kilohertz. And then there's quantization, which is where you round your samples to particular steps. And to decrease the bit rate of your audio, you can squeeze on the sample rate and lose your high frequencies, or you can squeeze on the quantization and add all kinds of nasty artifacts. So instead, there's a bunch of audio codecs that try to make trade-offs between these, or that try to process the audio differently so that you don't have to make this trade-off explicitly. So like I said, AAC is a complicated codec family. This is just kind of to give you an overview of what's going on here. The first AAC standard came out in 1997, and they kept adding things and adding things and adding more things. So at the beginning, MPEG-2 AAC. When MPEG-2 first came out, they just made a couple of extensions to MPEG-1 audio, and they decided that was kind of their quick fix out the door, and they wanted to build something clean from the ground up to sort of take advantage of things that people had learned that weren't compatible with MPEG-1. So they came out with MPEG-2 AAC in 1997. It has 3 profiles. There's a low complexity profile, and then there's 2 obsolete profiles, main and scalable sample rate. We're not going to worry about those because I'm going to focus on things that people actually use. And they define 2 ways to transport it. Of these, only the first one, ADTS, is really relevant. So here's a block diagram of an HE-AAC encoder, actually. There's a bunch of things here, but you'll notice the blocks are colored differently. And the MPEG-2 encoder is the green blocks, and then all of the other colored blocks are things that they've bolted on afterwards. So I'm going to start by talking about these windowing and MDCT blocks over here. So one of the tricks of most codecs these days is to, instead of looking at values of the waveform in time, look at the frequencies present. So over here, on the top, I have a zoomed in version of a chirp, which is just when you start at one frequency and slowly move to another one, going from 500 hertz to 5 kilohertz. And here is the FFT down here, which has all of those frequencies. But I'm going to play that for you. Oops. I'll play it again because I was muted. So the FFT has all of the frequencies at the same time. But what you really heard was the low frequencies, and then the higher frequencies, and then the slightly higher frequencies, and the even higher frequencies after those. So there's a component of the FFT that I didn't plot here called phase, which sort of magically allows neighboring high frequencies to cancel each other out at the beginning and low frequencies to cancel each other out at the end. But if you start to ramp up the quantization, which I talked about, your phase is going to get corrupted and you're going to hear all of the sounds at once. And nobody wants that. The FFT has another problem where to take the forward transform, you need your last sample before you can get started. And to take the inverse transform, you need your last coefficient to get started. And it's n log n complexity. So not only is this not streamable, but its complexity grows faster than the length of the clip. So this is a problem. So instead, we can break the audio up into segments, or chunks. So in AAC, we call these frames. They're just blocks of audio. But disjoint blocks are going to have problems on their seams. And signal processing fancy math teaches us that it's going to create this hideous ringing. So instead, we should use overlapped blocks. But first, here's a demo of a really shitty codec that I wrote in Python that just takes chunks of audio, takes their FFT, rounds it, which is what quantization is, and then does the inverse transform. So this is the input. And here is my FFT codec. It doesn't sound very good. So instead, we're going to use this MDCT transform, which has some fancy properties. And I'm not really going to ask anyone to understand the math up here.
I need 2 more beers.
The point of it really is that, all right. It's just to show that it kind of looks like the video DCT and it kind of looks like an FFT almost. You're multiplying samples by trig functions and getting a frequency version out. But the FFT, if you give it n real inputs, you get n over 2 complex numbers out. Complex number has 2 parts, so it's really n in, n out. Makes sense. The MDCT, you stick n real numbers in, and you get n over 2 numbers out. And this seems kind of fishy. We know AAC is a lossy codec. Is this one of the lossy steps? Is this going to cause nasty artifacts? Well, it's not a lossy step, and it's not going to cause aliasing, because when you do the inverse transform, you get n samples back out. And if you overlap and add them, assuming you choose window shapes that are appropriate, all of the artifacts from the subsequent block will cancel out the artifacts from the previous block, which is really neat. And I'm not going to prove that because that would take like an hour. So you're just going to have to take my word on it. But basically, your window function, and windowing is just when you take your audio and you multiply it by like a certain shape. So before I was talking about a rectangular window, which is just taking chunks. I'll get into the AAC window shapes in a minute. But just as long as your windows are constant energy, the math works out.
So what does MDCT mean?
Modified discrete, what does MDCT mean? Modified discrete cosine transform. So it's based on the DCT that's used in video codecs, only instead of based on a type 1 DCT, it's based on a type 4 DCT. And then it's the modification is the whole half the samples out, double the samples on the inverse transform.
So this is just a restatement of a mathematical statement of the Nyquist theorem, right? You're chopping out some of the frequencies that you don't need, but in the sampling domain? Is that
not quite. Basically, the way the math works out, it winds up sort of folding the outer terms and the inner terms on top of each other. And then you unfold those when you do the inverse transform. And the folding kind of cancels when you move on to your next block if you have overlap, which is what we want because we had those nasty FFT artifacts when we didn't have overlap.
Okay, so it's orthogonality between blocks.
Yes. So we can use a couple of different window sequences. I said we had a choice before. We have a long window, which starts at 0, goes to a maximum back down to 0. We have short windows, which look like the long window, only more compressed in time, and they're overlapped. All of the windows are going to be overlapped in practice. We stick 8 of them together, because each short window has 128 coefficients. So 8 times 128, 1024. The math works out nicely there. And then we have these two weird shaped windows that sort of exist to bridge the world between these two, between the long and the short windows. They match the long window, and then we need constant energy, and then they turn into a short window on the end. So here's a quiz that I'm not actually going to expect people to answer. But if an AAC frame has one 1024 coefficient MDCT window, how many audio samples does it have? So in a way, it has 2048 audio samples, because you do your inverse transform of 1024 coefficients, you get 2048 outputs. In a way, it also has 0 samples, because you don't have any valid samples until you overlap and add it with its neighboring frame. But if you're just operating an encoder or decoder in steady state, then what you get for feeding a frame in or pulling a frame out is 1024 samples. So, but if you're 1024 samples is what immediately jumps to people's heads, though, and if you're doing any manipulation of already encoded AAC, you really need to think about the other two, or you're going to create trouble for yourself. So AAC has two different window shapes as well. They have different signal processing characteristics. That's all I'm really going to get into on there here. The encoder chooses what shape it wants to use and just writes that down in the bitstream. And the decoder just listens to what the encoder said. But if you have two different shapes and you're trying to overlap the windows and make sure you use matching windows, how does that work? So AAC adapts the second half of your window to match the first half of your next window, which solves the problem. But again, if you're cutting AAC or doing something like that, you need to make sure that what was expected as the second half of your window actually is the second half of your window when you plug whatever you're gluing on there. So the reason why you would want to switch to the short windows here is that the frequencies are changing very rapidly, because like we said, we don't want the frequencies changing inside of our windows, or else we're going to get artifacts. So that was the windowing blocks. So now I'm going to talk about the psychoacoustics, which kind of control the rest of the encoder. And actually, they control windowing too. It's just a little bit separate. So human beings don't preserve the same sound pressure as equal loudness at all frequencies. We're much more sensitive to a little bit of sound pressure in these kind of medium bands between like 500 hertz and 5 kilohertz than we are on the outside.
So you mean it's a lot louder when it's...
It's a lot louder in those medium...
Yeah, okay.
If you just took a machine that's measuring the air pressure, which is what sound is again, for something that sounds very quiet, you know, at 8 kilohertz, that's going to sound very loud at 500 hertz. But beyond this, the actual contents of the audio affect what we perceive. So if you have a strong component, it's going to mask out weaker components nearby. So that's one trick where AAC can start to be lazy and remove things. This phenomena just doesn't happen at the same time. It also happens across time. So your masker also will mask out a bunch of stuff that happens after what's going on, which kind of makes sense. It's like when you go to a concert and you can't hear anything after. But it also masks out a little bit of what's going on before, which is kind of strange. It's like you can't hear before you go to the concert. But the pre-masking is a lot less than the post-masking. So you need to find a way to deal with the pre-masking. And MP3's big flaw was it doesn't have a way to deal with this pre-masking. AAC's short window is shorter than an MP3 short window, but it also has a second trick up its sleeve to mitigate those. TNS. So TNS is short for temporal noise shaping. It does a lot of signal processing on the frequencies in the encoder and then reverses that in the decoder. And it sort of pushes all of your quantization noise into where the loudest part of the signal is, where it's going to get masked out. So this tool is how most AAC encoders these days try to mitigate pre-echo. All right, so I talked about the psychoacoustics and I talked about this TNS thing. So next is the quantization and scaling. So I talked about quantization a little bit at the beginning. But first, what AAC does is it partitions the spectrum, which is just your range of frequencies, into a set of bands, 49 bands at 44 kilohertz, which makes sense because the threshold of what we hear is different at different frequencies. Then each band gets its own, what AAC calls a scale factor. It's what in video land is a quantizer. So that just basically says how much resolution you have at that band. And there's a fancy dequantization formula, but then each band is assigned a band type where you get to choose if you're going to Huffman code these, if you just want to zero all of them out, or if you want to use a really fancy processing tool where you copy from somewhere else. Huffman coding is just you take a variable length of bits and you decode those to some sort of value. So AAC has a couple of processing tools. I mentioned them on the previous slide. It has some stereo processing tools, mid-side stereo and intensity stereo. Mid-side stereo, the idea is instead of coding L left and right together, you code left plus right and left minus right because they're very similar often. And intensity stereo, the idea is that you just copy whatever is in the other channel, but you can scale it up or down, which can help for things like crossfades. So both MS and IS are per scale factor band, which was how we had partitioned the spectrum before. So each band you can choose if you want to use MS, you want to use IS, or you want to code independently. So now the bitstream format of AAC. So the actual bits that get spit out by the encoder have a high-level structure. And actually, this structure has been copied by a couple other codecs, like AAC, which is Apple's lossless codec, uses the same structure. You have a 3-bit syntax element name, and then you have a 4-bit ID tag that gets attached to that name. And then you have whatever the payload is for this element, and you just keep repeating that until you see an end-of-frame flag. So you can have a single channel element, which is just one channel of audio. You can have a channel pair element, 2 channels. Then you can have this coupling element, which is obsolete, so I'm kind of going to skip over that. And then you can have an LFE element, which is like your 0.1 and 5.1 or 7.1. It's just a single channel with some additional restrictions on top of it. Then there's a data stream element, because who hasn't said, I have an audio codec and I want to just smuggle arbitrary data through this? And then there's a program config element, which can tell you how all of the channels are laid out. And there's a fill element, which can be used to pad up to hit your bit rate or whatever. But the fill element has this neat property where it says that the size of the element up front. And none of the other elements do this. So if you want to add a new feature, the fill element's the way to go, because decoders that don't understand it can just skip it over. And then, of course, the end element, which I mentioned. So an example down here, we have a single channel element, 2 pairs, and then an LFE. So that's a frame of a 5.1 AAC audio stream. And the channel pair elements, since there's 2 of them, they have unique IDs. So AAC has kind of a crazy channel model. There's pre-baked configurations for 1, 2, 3, 4, 5, 5.1, and 7.1 channels. And then you can come up with something like crazy and freeform if you want. You can use the PCE to divide the listening area up into zones. And it just starts at front center and works its way around. And you just say how many speakers you want in each zone. Since there's 4 bits for the element ID, you can have 16 single channels, 16 pairs, so that's 48 channels, and then 16 LFEs, so that's 48.16. So that gives you a little bit of room to play around.
What is the dot?
So the dot means that this is sort of a low-frequency effects channel that's generally targeted towards a subwoofer in a normal system. In super crazy systems, they may have a pair of subwoofers and things like that. But in general, it's just sort of all your booms and whatnot.
Is there a standard of what frequencies get included there, or can you impose arbitrary frequencies?
So AAC, I think, imposes a limitation of what you can encode as an LFE of maybe half the sample rate that's normally allowed. But in practice, people go much lower than that by convention.
Is there phase information, any conventions around phase? Because it seems like multiple low channels would just have dead zones.
No, there isn't, which is kind of trouble. So I mentioned the ADTS transform, or ADTS transport rather. This is the header format on like a raw AAC stream. And I just really want to point out here that it's kind of friendly and also point out a couple of the warts that come back to bite us. So I mean, I've spent hours digging around through these headers and hex editors trying to figure out what the fuck is wrong with my system. But there's a sync word up front, so you know where the beginning is. There's a profile number, which only has 2 bits, which is going to be a nightmare in a minute. And the channel configuration is 3 bits, which is why we skipped 7.0 on the previous slide. And you can actually pack up to 4 AAC frames per ADTS header. If you're using AAC and transport stream, you have to encode it as ADTS. In MP4, you're not allowed to encode it as ADTS, but there's plenty of streams out there that are ADTS in MP4. It also has the frame length, which is really useful for debugging. So 2 years later, MPEG-4 audio comes out. They haven't really had a lot of time to work on this. MPEG-4, they said their primary focus was low bitrate streaming, but their real focus was sort of building a rich interactivity layer, kind of like Adobe Flash, which wasn't really popular yet at the time. So in MPEG-4, everything is an object. In MPEG-4 video, who needs a video frame when you can have a video object plane? In AAC, what happens is all of the profiles from MPEG-2 become audio object types, or AOTs. So they also take AAC and all that quantization and scaling stuff. They swap that out with 2 other subsystems if you want to use them. One of them is called BSAC, which is used by Korean broadcast. And one of them is TwinVQ, which isn't the late 90s TwinVQ. It's like somebody glued that to AAC.
Well, that's not the same TwinVQ.
No, it's not.
Why would it be?
So it also creates a unified audio framework where you can mix in synthetic codecs and speech codecs and all of those wonderful fake codecs that nobody uses. It comes up with this PNS tool, which is kind of cool. It uses a custom band type, and it has a scale factor for that band. But rather than having MDCT coefficients, it says just what the energy level is, and the decoder fills it in with randomness and scales it to that energy, which is great for like the super uncompressible HBO intro. So it also adds a tool called LTP, which stands for long-term predictor. This was an attempt to fix the main profile that nobody used, and once again, nobody used this. So it comes up with a new header format because you have to code now all of these synthetic things and the weird entropy coders, and there's way more than 4 AOTs, and they only saved 2 bits in the ADTS header. So they call it audio-specific config. It's the header that's nested inside the ESDS box in MP4, and it also winds up getting put in LATM, which is kind of a generalized transport format for raw streams and transport streams where ADTS can't be used.
What did you say, Matt, regarding RTMP?
Oh, yeah, RTMP uses the LATM.
Yes, RTMP uses LATM. If you're doing any of the super low delay variants, which I'll get to, they use LATM. So we've kind of cleared out all the green boxes and the red boxes, which is good, because that's most of the boxes on the page. HE-AAC is these blue boxes, and what I really kind of want to draw your attention to is they're kind of sitting way outside of the codec. They take place before windowing ever happens, and they just dump bits straight into the bitstream without bypassing the rest of the tools.
Using the data frame header or using some new proprietary?
I will get to that in a minute.
All right.
So how HE-AAC works is you encode your low frequencies as AAC LC at half of your target sample rate. Then you set up this crazy time frequency grid from the fully decoded output of your decoder. This grid basically just says you get 32 time slots, so 32 points in time, and each point in time you're looking at 32 frequency ranges. And what it does is it fills the high frequencies in from that low frequency data, and it has some parameters to guide it. But it's spending most of its bits on the AAC LC at half the target sample rate and just a few bits on the guiding parameters. So to do that, it winds up delta coding things from frame to frame. So it has keyframes, and these keyframes usually aren't signaled in the container, which is a brilliant idea. The thing that's actually brilliant about this, though, is normally when you've just squeezed too hard on your codec and it can't perform at the bit rate you're working on, one of the first things people do is they cut the sample rate in half. And HE-AAC operates on that principle, because you're encoding at half of the target sample rate. So it's kind of already what people were doing to cope with not having enough bits, only now they have a way to get the rest of that quality back. So here's an AAC, or here's an SBR, which is the tool that HE-AAC adds. It's called spectral band replication, is what does this fancy generating the high frequencies. And it sits around the rest of the AAC codec. So it has nothing to do with AAC in any feasible way. A company came up with this. They were called Coding Technologies. They were in Sweden, and they just tried to glue it on every codec they could find. They tried to do a version with MP2 for broadcasters. They tried to do a version with MP3 called MP3 Pro, if you vaguely remember that. And it took off with AAC. And here's kind of a diagram of the processing again, where you choose your crossover frequency, which is less than half of your sample rate. You encode that as AAC LC. You repeat it, and then the SBR parameters will try to massage these shapes here kind of back into that envelope over there. So HE-AAC worked out really well. So why not do the same thing for channels instead of sample rate? So HE-AAC v2, it works by encoding as HE-AAC a mono mixdown, and then you save a couple of bits to try to reconstruct the stereo. And I'm using the word try on purpose. So how it kind of works is this QMF analysis has already happened. It's kind of taken place by the SBR. So it breaks out the lower frequencies in a little bit more detail. Then it creates a decorrelated copy. And the idea behind that is that this audio source, it's bounced off that wall and off of this wall and off of everything. So it's just kind of coming to you from a different path.
Is it temporal decorrelated or hybrid decorrelated?
What?
Is it temporal decorrelated or hybrid decorrelated?
Steve asks, is it temporal decorrelated or hybrid decorrelated? I think it's hybrid decorrelated, but I'm not sure. It's been a while since I implemented this.
Okay.
So once you have the original signal and the decorrelated copy, each channel can choose how much of each version it wants. And you can have you can have zero of both if you're trying to do a crossfade or something like that. You can have some of both. You can have a lot of both, just whatever you want. And then so once you've chosen how much of each you want, you flatten it back out into time. And that's it for HE-AAC v2. One takeaway is the only thing that HE-AAC v2 brings to the table is this mono to stereo trick. Once upon a time, I had a boss who asked me to do HE-AAC v2 mono, and I...
Yes, right away.
So here is a graph of perceptual quality versus bitrate. This is from that company, Coding Technologies, that invented the HE-AAC stuff. AAC Plus was an old name they used for it before it was standardized. So what happens is at very low bit rates, HE-AAC v2 does very well. And then at a certain point, it stops contributing. And the reason these lines don't actually cross each other is sort of a technicality where the HE-AAC v2 profile includes HE-AAC v1. So it's like, this is HE-AAC v2, but it's not using any of the v2 features. And the same thing happens again for AAC LC and HE-AAC v1 around 100 kilobits. So if you're operating at very high bit rates, you're better off just using AAC LC. Basically, what happens is the encoder gets more fine-grained control. This control costs more bits, but at a certain point, the coarse-grained control from HE-AAC doesn't help. All right. So HE-AAC is this crazy extension I mentioned. It was added on after. So there's a couple different ways to signal it. There's implicit signaling, which is a fancy way of saying not signaling. You just have the SBR and parametric stereo elements, and a decoder that is conformant is required to find these and do the right thing with them. There's hierarchical signaling, which is where you just declare it as HE-AAC v1 or v2 at the beginning, and you hope the decoder can handle that. Older decoders can't work with that. There's backwards compatible signaling, which has the original headers like implicit signaling, but then it has a little bit of a bonus header at the end. And, but you have to know how big your header is to do this. In an LATM version 0, they didn't include that. So there's this crazy compatibility matrix. For practical purposes, though, MP4 can support all of them, which is great. ADTS only does implicit signaling, and -264 requires backwards compatible signaling. So if you're remuxing HLS and dash assets and they use HE-AAC, you have to make sure that your system can sort out the signaling. So here's how the data is actually nested, which is what I think Steve was asking earlier. So HE-AAC v2, it does mono to stereo. So you start out with just a single channel element in your AAC layer. And then you have this fill element, and AAC LC decoders, they don't understand this, and they just skip it because it has the size up front, and then you have your end of frame, which is always nice. So inside the extension data, you have your header flag, because we said it has keyframes, and the header is the keyframe. Then you have a big data chunk, and then you have an extension chunk. You have to be able to decode the data to decode the extensions, and you have to have the header from a previous frame to decode the data. So you can't tell if there's parametric stereo until you have found the header. So you can't tell when you're joining the stream, which is kind of terrible. But then parametric stereo, which is HE-AAC v2, it just repeats the same pattern, because I guess they liked it with the header flag and its own header and the data. And it actually has its own extension box, should they have felt the need to nest yet another set of extensions inside it. So the HE-AAC standard is sort of for the VOD world. In the real-time communications world, they have a low delay version, AAC LD. They play with the Bitstream syntax. They shorten up the window. It's not super interesting. Then they have AAC ELD, where they come up with this crazy window. They add an LD version of the SBR tool from HE-AAC. This one is the codec that's used by FaceTime for audio. It's part of the Android SDK since Jelly Bean also. So just a final word in practical notes about AAC encoders, because periodically I hear people talk about what AAC encoders they're using, and I kind of cringe. Never use the built-in FFmpeg AAC encoder. It's terrible. The fact that you have to pass in strict -1 is supposed to scare people away. -1 is the constant for experimental, though, so people don't really realize that they're trying to warn you away from using it. Then there's a couple of reference-derived ones, and then there's FAAC. At typical bit rates, FAAC is worse than lame, the MP3 encoder, so that should ward you off. Nero has an OK encoder. They used to have a very good reputation, but they stopped developing it, and they've fallen behind in the arms race. The FAAC developers went to go work on the Nero encoder, which is why FAAC fell apart. And then In the good encoders world, there's 4 good encoders from 2 companies, 2 from Apple. iTunes and QuickTime use slightly different variants of their encoder. And then Fraunhofer has FDK and this MP4 fast AAC thing. FDK was part of Android Jelly Bean, but it's broken away into a standalone library. It wraps into FFmpeg. If you're using the FFmpeg world, you should be using this FDK encoder. If you're using Apple's authoring tools, then you should be using the QuickTime encoder. Stay away from all other AAC encoders. So that's it.
What is the licensing of the FDK encoder?
So the licensing of the FDK encoder is basically it starts off like a BSD license, then at the end it says, hey, by the way, Fraunhofer has some patents for this, and you probably should make sure you're up to date on that.
Yeah, there's a licensing group as well for the actual codec.
Okay.
In addition
So you don't have to enable non-free in your FFmpeg configure, do you?
I think you do.
Yeah.
I think you do.
Okay.
Steve?
What's the best and worst part of AAC?
So the worst part is all of the bugs from all of the dodgy encoders. There are encoders that'll code the LFE as a single channel element. There's Japanese encoders that decide they'll use a channel pair to do 1 channel in Japanese and 1 channel in English. There's encoders that recycle element IDs that expect you to find elements positionally. Everybody says, oh, I don't care about the bugs, and then they scream that their files don't work, and it's, well, your encoder has bugs.
There is no best component?
The best component is that it's everywhere.
Fair enough.
That's really its only saving grace.
It's kind of like H.264.
I think I like H.264 better than AAC in some ways. All right, that's it.